Okay, so in the last video, we looked at some Fourier series examples. Okay, so now let's look at some Fourier series properties. Okay, so these are going to be specific properties of the Fourier series that will allow us to obtain the Fourier series of a wider variety of functions based on Fourier series that we know for some simpler functions. And you'll see what I mean when we see some examples here. So let me just remind you what the setup is for the Fourier series. So f of t is going to be periodic with period t, okay, and fundamental frequency omega naught, which is 2 pi over t. Okay, and then the Fourier series of f is going to be the sum f sub n e to the j and omega naught t. Okay, and I'm just going to use some notation throughout this video and throughout the rest of the class whenever we're talking about Fourier series. Okay, so I'm going to use f of t and then this double arrow, f sub n, and that just means that f of t has Fourier series coefficients given by the f sub n's. All right, so f sub n is a function of n that tells you all the Fourier series coefficients. So those are, I'm just saying those are the Fourier series coefficients for f of t. Okay, so the first property is called scaling property. What does that say? Well, that says, all right, well, you told me f of t has these Fourier series coefficients f sub n. What happens when I scale f of t by some constant, a in this case? Okay, what can I say about the Fourier series coefficients of this new function, this scaled version? Okay, what would you like to have happen? You'd love it if it just means the Fourier series coefficients of f get scaled. And it turns out is exactly what happens. Let's try and prove it. So we get a, and then I'll just plug in what the Fourier series is for f. Okay, and now I can just bring that a inside. And now you can see we have a Fourier series representation right here. This is the Fourier series of a times f of t. Right? Because when we scale something by a constant, the period's going to stay the same. The period isn't going to change. Okay. And so this omega naught is still accurate. That's still the fundamental frequency for this function. And now here are the Fourier series coefficients right there, a times f sub n. So I'll just summarize that. So if f of t has Fourier series coefficients f sub n, then if I multiply f of t by a constant, the Fourier series coefficients get multiplied by that same constant. Okay, so that is the scaling property. And I think all the properties we do today are going to kind of follow a similar form. We're going to change our function in some way. This is kind of what I was talking about at the start. And then we're going to try and see if we can obtain the Fourier series coefficients of that new function in terms of the Fourier series coefficients of the other function. Okay, so here's the addition property. So actually for this one, I'm going to introduce another function. So we'll let g of t also have the same period t, the same as f of t. And I'll call the Fourier series coefficients g sub n. Okay, then we want to look at what are the Fourier series coefficients of the sum of f and g. And wouldn't it be great if the Fourier series coefficients of that sum are just the sum of the Fourier series coefficients of f and g? So f sub n plus g sub n. Turns out that is the case. So I'll write their Fourier series out. F sub n e to the j n omega naught t. And then here's the one for g. The g sub n e to the j n omega naught t. And now I want to combine these sums, and I can do that. And you can see here is where we're using that g has the same period, right? Because that would mean they have the same fundamental frequency. I want to make sure that's the case. So these two functions have to have the same period. I'm going to get f sub n plus g sub n times e to the j n omega naught t. And there you go. This is, again, the Fourier series now. This is the Fourier series of f plus g, of f of t plus g of t. And here are the Fourier series coefficients. So I'll just summarize it. So if f of t has Fourier series coefficients f sub n, and g of t has Fourier series coefficients g sub n, and okay, f and g have the same period, okay, we need that, or else we couldn't combine these terms like this. Okay, we needed that omega naught to equal that one. Okay, then what do we find? We find that the Fourier series coefficients of f of t plus g of t is just the sum of the corresponding Fourier series coefficients. Okay, so that's the addition property. Okay, let's do another one. Time shift, we have a whole bunch here. Here's the time shifting property. Okay, and a lot of these you'll see are very useful in problems as we do more examples, not in this video, but in the subsequent course of the class. Okay, so what happens when we time shift our original function, right? We have f of t minus t naught. So we're going to apply some time shift to our f. Well, let's write out a Fourier series based on the Fourier series of f, right? Well, what's going to happen? Well, where does this t appear in the Fourier series? Well, it only appears right there. So I just got to plug in t minus t naught right there in the Fourier series. So I'll get f sub n, e to the j n omega naught, t minus t naught. Now I want to try and make this look like a Fourier series. Again, we know what the period of this function is. All we're doing is time shifting. We're just moving the entire function in time. That's not changing the period. So I know this omega naught is still going to be the period of this function. So I can just split up this exponent so that I have f sub n, e to the j n omega naught t naught, but I need a negative. Right, so that is taking e to the j n omega naught and this negative t naught. And then what do I have left? I have e to the j n omega naught t. Again, look at this. This is a Fourier series. And so it has to be the Fourier series of f of t minus t naught, right? Because we have a bunch of complex numbers times e to the j n omega naught t. We know that omega naught is accurate because the fundamental frequency hasn't changed, so we just shift our function in time. So this is the Fourier series, and so those are the Fourier series coefficients. And we can summarize this property. So if f of t has Fourier series coefficients f sub n, then when I time shift my function, what happens to the Fourier series coefficients? Well, they actually get a phase shift. They get this angle shift. They get multiplied by e to the negative n, n omega naught t naught. Okay, that's what happens with a time shift. Let's keep going. How about what happens when we take a derivative? How does that affect the Fourier series coefficients? Okay, so we're going to take the derivative, put this function in here, the Fourier series representation. Okay, now we're going to bring that derivative inside the sum. It turns out in general in math, you can't always do that, but for our purposes in this class, we can here. Okay, now we just differentiate that. What do we get? Well, we're just going to get that same function, but multiplied by j and omega naught. So I'll group it nicely here. So we're going to have j and omega naught after we take that derivative, and then e to the j and omega naught t. And so yet again, here are the Fourier series coefficients of the derivative of f of t. You can see we're kind of following a similar procedure here for all these properties. So if f of t has Fourier series coefficients f sub n, then the derivative of f of t has Fourier series coefficients j and omega naught times f sub n. All right, great. Next one, what happens when we conjugate f of t conjugate? Well, we'll just conjugate the entire Fourier series. Now, the conjugate of a sum is the sum of the conjugates, so I can just bring that conjugation into every term. Okay. Now I'm going to get f sub n conjugate, and then e to the j n omega naught t conjugate is e to the negative j n omega naught t. Okay, so now this is not quite the Fourier series representation, because in the Fourier series, you can see I need e to the positive j n omega naught t. Here I have e to the negative j n omega naught t. So I got to do some more manipulation here. What can I do? We can see that the n values here go over all integers, all the way from negative infinity to positive infinity, every integer. Okay, so what can I do to try and get rid of this negative? Well, what happens if I just change all of the n's to negative n? Then instead of going over the integers in one direction, I'll go over all the integers in the other direction. That doesn't matter because we're just summing everything up, right? Whether I have a big long list of things to sum up and I start from the left and sum them up, or I start from the right and sum them up, doesn't really matter as long as I sum them all up in the end, which I'm still going to do. Okay, so we're just going to do a change of variables here. And whether I, again, go over them starting from the left or starting from the right, doesn't matter. I'm still going to go over all possible integers. Now I just have to change all of these negative n's, all of these n's to negative n's. So I'm going to get f, so negative n conjugate. And then now I have this negative n up there. So when I change n to negative n, the negative will cancel, and I'll just get j n omega naught t. Yeah, this is just a change of variables. I'm sure you've seen this before. Yeah, you can try out, some simple examples on the side to make sure you agree with this, right? Just maybe write out these terms from n equals, I don't know, -3 up to 3. Okay, and then write out these terms from n equals -3 up to 3 and make sure that they're the same. They will be. It's just written in a different order. Okay. All right, so this is what we get. And now this is nice because this looks like our Fourier series now, right? We have complex numbers times e to the j and omega naught t. So those are our Fourier series coefficients. So if f of t has Fourier series coefficients f sub n, and what happens when I conjugate f of t? Well, it turns out I don't just conjugate the Fourier series coefficients, I also put a negative n. I also have to change their index to negative n. Okay. So that's the conjugation property. All right, we have two more here. How about time reversal? Okay, what happens if I plug in negative t? I take my whole function and I flip it in time. Well, again, as we saw with the time shifting property, t only appears one place in this Fourier series, e to the j n omega naught t. Now I just want to plug in negative t there. So I'll just put a negative sign. And let's do the same trick we just used, right? Because now I have e to the negative something. I want it to be e to the positive that thing. So I'll just change n to negative n. And the sum, I'm still going to be integrating over all of the integers. Okay, really I'm doing kind of two steps. I mean, if you want, you could make this a little more step-by-step procedural and say, all right, I'm going to change n to like negative m, and then afterwards you could change like m to n or something, but I'm just kind of doing it all in one shot. Just going to change n to negative n all in one shot. Okay, just a change of variables. And so we're going to get f sub negative n, e to the, now this negative n, when I change n to negative n, it'll cancel, and I'll just get e to the j and omega naught t. Okay, and again, I encourage you, try writing out these terms like from -3 to 3 in both of these sums, and you'll see that you get the exact same thing. Okay. right? So that's what we have. And now, just like before, those are Fourier series coefficients, f sub negative n. So if f of t has Fourier series coefficients f sub n, then f of negative t has Fourier series coefficients f sub negative n. Okay, so that's kind of nice. All right, last one is time scaling. Okay, so now what happens if I scale the time argument? So let's say I scale it by some number a, and we're going to have a be positive. If a were negative, if you want to do a negative scale, of course, you could just, apply the time reversal to get the negative sign after you scale it by a. Right? So you can combine these two properties to account for any scale factor multiplying that t that you want. Okay, so what happens here? I'm going to have f sub n, e to the j, n omega naught, and then I plug in at now, right? Because that's the only place this time argument appeared. So I put an at right there, f of at. And now I'm going to do something a little different that we haven't quite seen yet. And I'm going to write this as f sub n, e to the j, n, and then I'm going to put the a with the omega naught. Okay. And why am I doing this? Well, in all of the cases we've seen so far, the operation we applied didn't change the period. But now we're actually we're scaling the time argument, so that would change the period. So let's try and see how the period is affected. Okay, so we have f of at. Okay, now I want to shift that function by a certain amount. Okay, and I'm just gonna kind of show you that this amount is what we want. Okay, so let's shift that function by t over a. So that big T is the period of f from before, from originally. Now I'm dividing by a. Okay, so this is really like some function, maybe g of t. And now I'm just doing g of t plus t over a. Is that. Right, and now when I multiply this through, I'm going to get f of at plus a times t over a, which is just big T. But now we know that that equals f of at, right, which is just g of t. And this is because f of t has period t. Okay, so when I shift f by that amount t, I get back the same function I had before. Okay, so I'm going to erase these g's because we don't really need them. That was just to explain what was really happening. But all we have here is that when I have f of at, a new function, and I shift it by t divided by a, I get back the original function, f of at. So what does that tell me? Well, it tells me that f of at has period t over a. So we know it's periodic with t over a, okay? But then using the fact that this t was the period of f of t, we actually know this is the smallest amount I can shift because this is the smallest amount once I get to this step that I can shift by in order to get back my original function. And so we kind of rigged it up to work out that way. Okay, so f of at has this period t over a, and the fundamental frequency, okay, is going to be 2 pi divided by t over a, which is just a times 2 pi over t, which is a times our original omega naught for our f of t. So overall, what's happening? Well, when I scale the time argument by a, what happens to the period and the fundamental frequency? Well, the period gets divided by that a, okay, and this is for a positive a, and the fundamental frequency gets multiplied by it. Okay, so that's how affecting the time argument changes the period. And why do we need to go through this? Well, we need to go through this to say, hey, wait a second, this actually already is the Fourier series for f of at, because this a omega naught is exactly what I need in that position. I need the fundamental frequency of f of at. Let me just write that down. So this sum here is the Fourier series for f of at. Okay, because the Fourier series is the Fourier series coefficients times e to the j n omega naught t. And omega naught for this function, you can see the fundamental frequency for that function is a times the fundamental frequency for f of t. Okay, and so that means that these f sub n's are actually the Fourier series coefficients for f of at. And this is a little weird the first time you see it, maybe. Let me just write it down. So if f of t has Fourier series coefficients f sub n, then f of at, a is positive, has Fourier series coefficients that are what? Actually, f sub n as well. But you got to remember here that the period is t for the first function, and the period here is t divided by a. Okay, so it's a little strange. It comes from the fact that these Fourier series coefficients don't actually have sort of the frequency of the function built into them. They're just indexed by these integers. Okay, so it turns out that this is one consequence of that, that when I scale the time argument by a positive number, the Fourier series coefficients actually don't change. These f sub n's do not change. The thing that changes is up here in this exponent, the fundamental frequency changes. Okay, so that is that property, the time scaling property. And in the coming classes and discussions and so forth, we'll see many different example problems using all these properties. You can get a lot of good problems out of them. All right, so that's it for this video, and I'll see you in the next one.